Hey guys, this is Khalid. I just want to give you a quick overview of imaginary numbers and try to get some of the insights behind it. Imaginary numbers are often really confusing, and people say, "Oh, it's used in advanced science classes, and you don't really need it." But really, the key concept here is imaginary numbers are no more difficult than the second dimension. We're used to numbers being one-dimensional, and imaginary numbers let us take numbers into the second dimension. So that's kind of the key insight, and then we sort of jump into the intuition. My favorite way to think about imaginaries is actually to step back and think about negative numbers. When negatives came out, they weren't really liked. People thought they were weird, they were crazy. Famous mathematicians thought that they looped around past infinity. So the way you got to the negative numbers is that you started with 1, 2, 3, 4, you went to infinity, you went past infinity, and then it circled back to the negative numbers. So that's sort of how you got to the negative numbers there, because they didn't really have a good insight or intuition about what it was trying to represent. But I think we've come to understand that negatives can kind of represent the opposite of something. So if having money is being a positive number, then owing money is a negative number. Or if going north is positive, then south is negative. So once this intuition of opposite came about and numbers can be the opposite of each other, well, the negative numbers started to click, and now it doesn't really give us trouble. The problem is imaginary numbers, well, we don't really have a good insight for it yet. Today we'll get one. But for hundreds of years, people thought of imaginary numbers as something weird. And in fact, it's called imaginary because they didn't think it could exist. It was an insult. So it's kind of strange for us just to tell you about imaginary numbers and then not explain the history that, hey, it's called imaginary because people had a really, really hard time getting it. But that doesn't mean that we can't understand it today. Um, the the main thing that you want to think about is what does it mean to square a number. So, you've probably seen that I squared equals -1, but what does that mean? Well, let's take a step back. When I have a simple equation like x squared equals 9, what I'm really saying is I start with 1.0, I multiply it by x, I multiply it by x again, and then I get 9. Right? Because x squared equals 9 is really the same as 1 times x squared equals 9. So you start with 1, multiply by x again, and we get 9. So the question is, okay, what x would give us 9 after applying it twice? Well, if we have 3, we go from 1 to 3, and 3 to 9. Or if we have -3, we go from 1 to -3, then -3 to 9. So the idea is, okay, what transformation, what sort of change when we apply it twice could get us to 9. And that's sort of what x squared equals 9 represents. Now, when we say I squared equals -1, it's sort of a similar concept. We're saying, okay, we're starting at 1 again. We want to get to -1, but we need to do it in 2 multiplications. Okay, so we have 2 steps, each by I, and we want to end up at -1. Now, normally we think that's impossible. We say, well, 2 positives is positive and 2 negatives is positive, so there's no way to do it. But we're not being creative. The question isn't whether or not to use positive or negative numbers. It's to say, can you do 2 multiplications and have that result be -1? And we can, actually, if you think about it a little bit, can you take 2 operations and get from here to here? So you're facing forward. Can you get backward, but can you do it in 2 steps? Well, there's an answer, actually. The answer is a rotation. So if we start here, rotate this way, and rotate again, that was 2 steps, and we went from forward to backward. So when we say that I squared equals -1, we're really saying, well, you start at 1, apply I, which is a rotation, apply I again, and you're pointing negative. Now the neat thing is that you can rotate up or down, so there's actually 2 square roots to -1. You can apply 2 rotations to the top or 2 rotations to the bottom. And by convention, we call the top rotation, we call that positive, and the bottom rotation, we call that -I. So those are just 2 different ways to get to the same endpoint. So this is really the key insight here. I is the imaginary dimension, and multiplying by I is what puts you into that imaginary dimension. Just how -1 is sort of a backwards direction, and multiplying by a negative puts you into that backwards direction. In general, when you multiply a number, you're sort of giving its properties to the result. So you start with 1, which is this plain old regular number. When you multiply by I, the I-ness kind of gets infused in there, right? So now you're in the imaginary dimension. So with this insight, what can we do? This is really the key kind of metaphor that you want to think about? Well, one of the first things you can do is find patterns. So you might be aware that with negatives, if you keep multiplying them, they kind of toggle back and forth, right? So you have 1, negative 1, 1, negative 1, 1, negative 1. It kind of toggles back and forth. With I, something similar happens. You start rotating. So you have 1, I squared, I cubed, I to the fourth. Oh, you're back to where you started. It's just like any kid can tell you, 4 left turns is the same thing as not turning at all. If you keep applying I, you sort of rotate around in a circle, and the idea is that your rotations end up canceling out. Every 4 rotations is the same as not rotating at all. So I has this pattern of straight or positive I, negative, negative I, positive I, negative, negative I. So when you keep repeating that pattern, that's sort of what you get. So when someone asks you, what's I to the 50th power? Well, you can sort of work out how many rotations that would be. And in that case, I'd say, oh, okay, well, 48, let's see, yeah, 48 is divisible by 4, so then you have 2 extra rotations. So I to the 50th would be negative 1, because 48 times you're going around, and then 1, 2 is the kind of the remainder. So that's how you intuitively think about this little pattern that we see here. Now, again, this is sort of just the beginning. There's this extended idea of complex numbers, which is basically I is sort of a pure rotation. So you started here and you rotated all the way straight up. What if you didn't rotate all the way? What if you sort of went 45 degrees? If you went half and half, then that's called a complex number because it's sort of complex actually means not just hard to understand, but complex means something that's made of two things or multiple things. So you're made of a real part and you're made of an imaginary part. So when we talk about a complex number like 1 plus I, we're saying this number has part of itself in the real dimension and part of itself in the imaginary dimension. And the way I like to think about it is kind of silly, but it's my little analogy, is that it's like you have a hot dog, right? And you can have ketchup or mustard or a little bit of both. There's no reason you need to have only ketchup or only mustard. If you want a hot dog with half and half, great. Or all mustard, great. Now, normally we're used to ketchup. That's the real numbers. We're always getting ketchup. But you can mix in a little bit of other spices and it's okay to have one or the other. So the idea for a complex number is that you have sort of a mix between the real and the imaginary. And in general, we can call that A plus BI. So instead of 1 plus I, which is exactly 50-50, it's a 45-degree angle because it's the same on both, you can sort of have any combination of A and B that you like. Now, the neat thing is, what does it mean to have the size of a number? Normally, when we're talking about one dimension, the size is the distance from 0. Sorry, the size is the count of it. But with complex numbers, there's not really an easy way to think about size, but the kind of the insight is that the size is really the distance from 0. So we start and we say, okay, how long does it take us to get to 0 from wherever our number is? And the number could be straight up, it could be diagonal, it could be all the way across on the real side. And the way you do that to find a distance is basically to take the Pythagorean theorem. So the way that you compute the size of an imaginary number is to say, okay, how far is it from 0? And let's take the Pythagorean theorem to figure that out. So it looks like this, square root of a squared plus b squared, where a and b are the real and imaginary parts. That is how we get the size of a number. Now, that's sort of my quick, super high-level overview. You want to go practice it on other websites. There's Khan Academy. There's a lot of places where you can go and work on these things. One example that I like to use, which I haven't seen very often, is actually rotations. Now, a lot of examples, they sort of give you these algebraic problems, which is okay, but I like to make real-world problems. So one of my favorites is how to rotate shapes. So here's my little example. Let's say you're kind of a tugboat captain, like I'm sure you aspire to be, and you are on a trajectory. Your current trajectory is 3 across, and 4 up. So what does that mean? You're going 3 miles, let's say, east and 4 miles north. That's sort of your trajectory. You're kind of just going on your ship. And now the captain tells you, or I guess you're the captain, you decide that you want to turn the ship 45 degrees. Okay, that's fine. You just want to turn it 45 degrees. You're on some heading, and you want to turn it. What is that new heading? And it's actually kind of a hard problem. If you don't know anything about imaginary numbers, how would you figure this out? I mean, really, like, okay, I'm on 3 and 4. Okay, this This is my heading, and I want to turn it 45 degrees. What is that new heading? You can give me an angle if you like, or you could give me a new, a new trajectory. That's fine. But without a calculator, it's actually kind of difficult because what do? You just don't have much to work with. But we have imaginary numbers to the rescue. Basically, the properties of imaginary numbers, like I said, is that when you multiply, you're sort of giving, you're infusing the result with your kind of your essence. Is kind of getting mystical, but you're giving your properties to the result. So when you multiply complex numbers, you're actually the thing that's being multiplied in, that actually rotates. It gives its rotation to the result. So if you have a trajectory here and you multiply in 1 plus I, you're actually giving that 45-degree angle to the result. So what happens is when you take 3 plus 4I, multiply it by 1 plus I, it's almost as if you're putting that little triangle there to get that new angle. And when you multiply and you cross multiply it out, you actually get negative 1 plus 7I. So this is actually the exact trajectory that you're going to be on. You're on 3 plus 4I, you multiply it by 1 plus I to get that 45-degree angle, and you know what? That trajectory, the new one, is negative 1 plus 7I. So that's really cool. We figured out kind of a real-world trajectory problem using imaginary numbers. No trigonometry, no calculators, just all in our heads, and we can do it out on paper this way. And believe it or not, this is actually what people use in video games for rotation problems quite often. There's actually four-dimensional numbers that they use called quaternions, which are actually used to model rotations. So imaginary numbers, you don't need to do crazy physics. There's actually real-world problems that you can solve, and it's because you're using the second dimension. We've been stuck in kind of this linear, flat, squished zone, but the truth is that numbers can be more complex than we thought. So we actually have this one dimension here, and we can add in this other dimension, and we're free to go. And you can add more and more and more. And just think about what might happen. Are you going to run out of letters? You might. So one idea then is to say, okay, well, if we want to have a huge number of dimensions, maybe it makes sense to write down our numbers in a list. And hey, we can call that list a matrix. So that's sort of the jumping off point to having more than a few dimensions. Anyway, this is kind of my key insight about I. It's a way to think about numbers in 2 dimensions. It's a weird concept. It was insulted when it came out. It was called imaginary, but that's because people didn't have a good intuition. And you know what? It was, I think, 40 years after imaginary numbers came out that people thought to make it a 2-dimensional analogy. And because of that, they really understood it a lot better. So, don't feel bad if you don't get it. These are hard concepts. This is PhD level stuff, 300 years ago, and you're understanding it now. And the key is just to have the right analogies in your brain. I is a new dimension that numbers can be in. Even though we're used to plain old ketchup, we can add a little bit of mustard, spice it up a little bit. I is this new dimension that is available to us if we want to use it for things like rotation problems. Anyway, that's my intuition. Go practice those problems. Happy math. Hey guys, not done yet. I have 3 little tests you can do to kind of check your intuition and make sure that you've really got the concept. Each is a little bit more tough than the first. Okay, here's the first question. What do you think the square root of I could be? Knowing what you know about how I works, what do you imagine the square root of I would be? Do we need a new dimension for that, or is it something simpler? Okay, next question. What do you think the cube root of negative 1 could be? So again, if I is getting to negative 1 in 2 steps, what do you think the cube root of negative 1 could be? And how many cube roots are there? Last question. This one's kind of tricky. What do you think raising something to the I power could mean? It's kind of a weird concept, but if we think of exponents as growth and I as rotation, what do you think raising something to the I power could mean? Hopefully these questions become more comfortable to you, and when they do, it means you have a really solid intuition. Happy math.